Anyway, okay, so basically today we will continue our journey to exploring the deep neural networks. Okay, so the concepts of neural network we adopt so far still fall into the category of feed-forward network or fully connected networks. It's not a convolutional neural network. It's not a special type of network structure, network architecture, but it's a very regular feed-forward network. But many of the concepts like the momentum, the RMSProp or the atom techniques to train the neural network efficiently, they apply to different types of networks. So basically to all types of neural network-based models, we can use these techniques, okay? Because the essence or the nature of these techniques deal with the numeric properties of the gradients computed, okay? So it's strictly speaking, it's more the theoretical basis for these techniques. They are more mathematics, but not from the side of computer science. Okay, so it's a lot of theories in optimization theories involved, like how do we find the proper path from the initial points to the minimum points, like effectively or efficiently. So these are more into the realm of mathematics, okay? But the computer science tools, like the programming tools we have right now, allow us to quickly adapt these techniques without worrying about the implementation details. Okay, so as a brief review of the previous contents, nowadays we basically use atom as an algorithm, as a tool to for experiments, for training the neural network models, because it is fast, okay? But still, if there's some like weird behaviors that we have observed while using atom, then a lot of people will choose to, or a common choice is to use, to backward, to use the raw gradient descent method. So this in this stochastic gradient descent class, okay, it's a very primitive way of updating parameters just using the gradients. Okay, so although we can set up the momentum term for it, but still this term we can make it small or make it big to control the degree of momentum that we want to compute. Okay, so this method, SGD method, is a safer way, I would say. It's a more primitive. It just uses gradients to update parameters, while in atom, it's a combination of the momentum and the RMSProp, which is, in most cases, it's a better choice, and it's a fancier technique that almost certainly converges faster than SGD, okay? But if you prefer something safe, something primitive, and something that is more interpretable, then probably SGD could be your first choice. All right, that's the technique that we deal with the network about gradients, about tuning the gradients to make it training fast. Yes, the learning rates, the LR here in the parameters, it refers to the learning rates. And here exactly what we are gonna talk about in the next slide. So learning rates also is a critical factor that determines the the speed, training speed, okay? So the general principle when we train a neural network model is that we want to slowly reduce the learning rates, to reduce the alpha over time while we train the model, okay? Because the general reason is that the mini batch gradient descents will never actually converge to the theoretical minimum points, okay? Because mini batch uses part of the data, a proportion of the data to compute the gradients. It's never the theoretical perfect minimum points, okay? So, and the property of a lot of the cost function in the space of the cost function, when we're approaching the minimum points, the gradients will become, if we still take a too large step around the minimum points, it's likely that we're gonna miss the minimum points, okay? Because the actual gradients would be small, rather small, very small values around the minimum points. So we also need to adjust the step that we take around the minimum points. And that is basically the reason why we want the learning rate to decay over time. So that's as the results of the training indicated by these green curves. As you see, we take bigger steps in the initially, and then we gradually reduce the steps, because that will make sure that we will not deviate too much from the theoretical minimum points, okay? And the learning rate decay is almost a default option in nowadays when people design programming the way model are trained, okay? And there's a variety of choices if we look at the mathematical tricks behind this decay, and it's quite straightforward, okay? So we can use the epoch number to indicate the current current progress of the training. So one epoch means one complete pass of your total training set, okay? So we usually go through the total training data set for multiple times, like 5 times or 10 times or even more, 20 times. So we can use the epoch number to indicate the current progress we're making. So the first epoch means we are at the early stage, and the 10 epochs, maybe it's a very late stage. So we want the alpha to decrease while the epoch number changes. So this is a quite straightforward way to control how fast the alpha should decrease, okay? And the decay rate is some constant that we can predetermine as some hyperparameters, okay? And also, the alpha 0 is the initial learning rate. So about the initial learning rates, I can probably talk about more about it because it's always a myth or it's always brings discussion about how to set the initial learning rates. So ideally, it's hard. So, okay, I see the question is the decay rate typically set to 1. So for that, I don't know for now, because for different problems, the decay rate is very different. And it's just like the initial choices for alpha 0. So for some problems, and for some different data sets, if the data is very big, then probably you don't need to use that many epochs, and probably in that case the decay rates can be set up to a smaller values, okay? But it's a very empirical choice, and I would say the usual practice is that you apply the default values provided by programming frameworks, okay? Or if you want to replicate some existing models, then the original paper, the hyperparameters that they have, the authors have chosen is the best way to stock this. Okay. So if we choose decay rates as 1 in this particular example and alpha 0 as 0.05 as the initial values, then in each epoch, we will have a different learning rates. Okay, so that is one option. And usually we can also use the exponential way to decay the learning rates. Like we use some value, some number like 0.95, which is below 1, to compute the exponential function with epoch number as the index. Okay, so in later epoch numbers, the coefficients, the resulting coefficient would be a smaller value. So this is also a typical choice. Or we can make a square root of the epoch number and then put it as the denominator. So there are a bunch of different ways. Or we can, instead of using the epoch numbers, so if we think, if we're gonna just train the model with just one epoch, but we want to adjust the learning rates within that one epoch, then we should not use epoch number, right? We should use the iteration number, like the t indicated by this t. So within one iteration, we feed into one mini batch of the data. Okay, so probably in the next mini batch, we can slightly change the alpha, the learning rates, which is also a possible option, because when you don't want to go through the whole data set for many epochs. Okay, so this is about the learning rates. And now in practice, when we use Pytorch, it provides some convenient functions to use. It's called learning rate scheduler. And I found this is, in my experience, I found this is quite necessary, as if we want to reach a better effect of convergence, or better training accuracy, or lower training loss, these learning rate scheduler is almost a must. Okay, so in the example I shown here, I caught something like stepwise learning rates decay. Okay, so it's more like based on the number of epochs. Okay, so it basically for iterations that are within the first 30 epochs, it will use some fixed learning rate, but within the next segment of epochs, it will use a relatively much smaller learning rates, and so on. Okay, so I didn't find a very big difference by comparing the stepwise learning rate control versus the exponential way of learning rate decay. So probably because the problem that I'm looking at is not a complex model. Okay, so anyway, the resulting training loss from two ways of control learning rates, they don't differ that much. But that said, they always outperform the the primitive or the raw training method without controlling learning rates. That is almost for sure. Okay. All right, that's the learning rates decay, and we just quickly go through it. Okay, so next we're gonna look at some regularization techniques for deep neural networks, which is a important topic here. So we're gonna review the L2 regularization for linear regression and logistic regression first, and then we'll introduce a special type of regularization technique called dropout. And this is a very efficient, very effective way of avoiding overfitting for deep neural networks. And there are some other techniques we will also cover for specific tasks. Okay, so one impression that we may have for deep neural networks is that it's a very big model. And a big model means we have way more parameters than simpler models. Okay, we have way more parameters than simple logistic regression, than simple or SVM models, say. So we basically want to lower the risks of overfitting to the training data, okay? Because more parameters means we can basically the model will have basically the capacity to memorize the singularity, the special features in the existing training data set, but it could doesn't generalize well to new data sets that are unseen or that never appeared in the training data sets before. So that is a very the risk we want to lower. Okay, so the overfitting, here's a figure to help reveal the concept of overfitting. So we don't want the model to be too complex so that it describes the decision boundaries between classes so well that it's avoided the misclassifications. But that is not the way we want it. We want the model to describe a general pattern. Okay, so when we talk about overfitting in logistic regression model, we use something called L2 regularization for logistic regression. Remember, the idea of L2 regularization is that we modify the cost function. On the left of the equation for logistic regression, this is the cost function or loss function to each training example. And we modify the cost by adding a L2 norm term. Okay, so the W's are the weights, are the parameter vectors. Okay, this W transpose times W is basically the L2 norm, which measures the magnitudes of the all the parameters in a model. So putting that L2 norm into the cost, and because we want to minimize the cost, so as a result, the L2 norms will also be minimized. And the gradients computed from this new cost has a new component controlled by the lambda and the W, right? The lambda controls how strong the L2 regularization is. So within each gradient, with each step of the gradient descent, we will update the parameters to a relatively smaller value because we minus alpha, the learning rate, times the lambda, and the lambda is a positive number. So this minus in turn will make the parameters to a less values with the smaller new values. Okay, so that is the result we want to achieve. We don't want the parameters to be too big because a parameter that is too big means we put higher weights to that parameter, which means the model is more complex. And a smaller parameter value means that a model is more simpler, it's much simpler or more vague, okay? So the thought is that we minimize the costs and the complexity. We want to simplify the models by constrain the parameters to smaller values. Okay, so we can actually do the same L2 regularization to a neural network model. Okay, because it is not that different, right? We both have, compared to logistic regression, a neural network is just a combination of a lot of neural nets, neurons. Neuron is a basic unit that accomplished logistic regression, right? So it's just a collection of these neurons. So why not we also modify the cost function for the neural network, and we can compute the L2 norms of all the parameters, right? From all the layers. So from layer 1 to layer L, we can compute the norms for the weight matrix, and sum up all the norms. Okay, so this norm is basically we take out each entry in the weight matrix and raise to the power 2 and sum up all the entries. Okay, which is not a fancy way, but it's just a regular way of computing the summation of a bunch of squares. Okay, so we have a mathematical term called Frobenius norm for a matrix. Okay, you can just memorize it by a summation of a bunch of squares applied to each entry in that matrix. Okay, so we do the same thing when we update the parameters. Okay, because we change the loss, so now the gradients would be different, controlled by this lambda. The weights, the new values for the weight parameters would be a smaller values. Okay, so this is the so-called weight decay. Okay, so the weight decay here refers to the fact that each time when we update the weights, it's decayed by some amounts controlled by learning rates and the lambda. Okay, so if we have bigger lambda, the weight will be decayed faster. Okay, so this is something in frameworks like Pytorch we can immediately apply. Okay, so in a optimizer defined in Pytorch, we can use the argument weight decay to define the strength of L2 regularization. So weight decay in Pytorch is just another name, an alternative name for the L2 regularization technique. Okay, so this technique would be useful when we want the model to perform better by avoiding overfitting. Okay, but it is not basically not a like must be or must choice. Okay, in my most recent experience using weight training a neural network based language models, it's actually a sentence classification models. I didn't see a lot of useful gain by setting up the weight decay. Okay, so actually I just found that the next technique, which we're gonna cover soon, the dropouts, is a more useful way to control the overfitting issue in deep neural networks. Okay, this might be more useful when the model is a little bit simpler. Okay, but in deep neural networks, people would use the dropout regularization technique. Okay, so the dropout, it got a fancy name, and I do think it's a fancy technique, and it comes with some profound philosophy behind the theory of neural networks. Okay, so what this dropout technique basically does is to hide some units during the process of training, or to, in another way, to disable those units, or to set those units invisible during the process of training. Like the word dropout means that we drop those units in the hidden layers. Okay, so after we, for example, in this network on the left, it's a very complete feed-forward neural network, right? If we drop out those red units to the right, then we will have a complete, it's a different neural network, right? With different hidden layers, with different unit counts in each hidden layer. Okay, so this would be useful if we say in probably I would say that in another way. So if we want the dropout to take effect on the training results, on the resulting model, we need to apply dropouts frequently during training, not just for one time. Okay, we want to apply randomized dropouts for the network throughout the training process. Okay, so we'll see later that's why this is necessary. Okay, so for example, let's look at the difference. This is a simple demo showing how dropout is applied to different input examples. So for this example 1, we drop out these 4 units, and the resulting underlying model is actually like this. And probably for the next input example 2, right, we will drop out the green units, which are the different parts of the network. Okay, and the resulting model will be a different one as compared to the model that deals with example 1. Okay, so here the effect is that we use 2 different sets of parameters to model 2 different examples. But that 2 set of parameters, they are not totally different. There's still some overlap, or I would say the majority of the parameters used are the same. Okay, but we make dropouts randomly on different input examples so that the parameters are slightly different when we model different data sets. Okay, and a direct result is that the models don't stick with particular data examples, or the parameters are not going to memorize the patterns in the data. Because each time when we go through the examples, the random dropout will make sure that the model will forget some information that it has picked up in the previous iteration. So it will learn something new about the data points, learn something new in the pattern, instead of memorizing or reinforce or enhancing the old memories. So that is some higher level explanation. So, and in details, we can, and in technical, from a technical perspective, the dropouts technique is always, is also easy to implement. And we don't, actually we don't need to do a lot of things to remove those units. We can actually use a mask of discrete elements, either 0 or 1, and use that masked matrix to multiply with the activations from all layers so that we can cross out or drop out the units with the corresponding 0 elements. Okay, and because the activation outputs for each layer, they are also matrices. So if we want to drop out some elements in that activation, we can simply use a matrix of 0 or 1, and to do a element-wise multiplication with the masked matrix with the result matrix. So the elements multiplied to 1 will be remained, right? Will be kept, while those elements multiplied to zeros will be zeroed out. Okay, there will be no activations for those zeroed out elements. Okay, and when we define the mask matrix, we should use some preset probabilities. Okay, so in this case, we set the preset probabilities to be 0.8, and that means 80% of the elements in the activation matrix will be kept, right? Because we use this random generator, the random class, to generate some random numbers, and between 0 and 1. And also we make sure the results have the same shape as the activation, as the matrix of the activations. It's the same shape. So this comparison with the probability number, which is a real number here, will result in basically a Boolean values. And in NumPy or in Python, the Boolean in NumPy arrays, the Boolean value with true values will be treated as 1, and Boolean with false will be treated as 0. And also, there's a normalization with this preset probabilities. So this divided by probability points by the preset probability is a way to basically scale up the activations a little bit, right? If you divided all the elements by some value that's between 0 and 1, all the values in the activation will be scaled up, because when we drop out some elements, the total values of activation will be decreased, will be reduced. So in order to mitigate that reduction effect, we want to scale up the elements in the activation basically to a higher level. I see a question: using random dropouts might have different hidden layer combinations. So would not that affect results in any negative way on the outcome? Okay, so that is the question that I'm basically I think it's the interesting parts about Dropout, because it makes the training it brings more randomness in the training process. So that means the zeroed out or the dropped out elements will be no longer carry any effects in this current training process because the activations are dropped. But this also is useful to make sure that the model will not stick to some certain fixed patterns in data. Okay, so the memories of the model, of the parameters of the model will not be enhanced by going through the same data patterns again and again. But it creates some variance or randomness in the data so that the model will have more flexibility in deal with unseen patterns or deal with new patterns in the data. So the performance of the model trained with random dropped outs will usually have better effects on the testing sets. It should have more flexibility in dealing with testing data that are never seen in the training example, in the training sets. So yeah, that is okay. I see another. Take less than 20%. So in this example, it's not exactly 20% of the nodes, but it's the probability threshold. Like the random.rand function will generate some a bunch of random numbers within the range of 0 and 1. Okay, so and that's the probability generated, the numbers generated from within 0 and 1, they have a uniform probability. So it's from a uniform distribution. So if we set the probability threshold to be 0.5, then when the outcome, when the inputs to the random function has enough numbers, it has sufficiently, is sufficiently big, it has a lot of numbers, then in theory we can find that almost 20% of the nodes will be dropped. Okay. So, and this the final step of dividing by the probability is called inverted dropout. It's basically a way to, without losing too much activation total amount of activations by scaling up the values to some higher values. Okay. So with this step, the total magnitude of that activation remains almost the same, as the previous way without using dropouts. Okay. Also, it makes testing time easier. So we don't need to scale up the testing data sets because the activations, they are scaled up during the training phase. Okay, so in NumPy, like here's an example showing the way that activations are dropped out by making some random numbers, right? So the mask generated by using this numpy.random function will be like a bunch true and false values, but the true and false values will be handled like 1 and zeros in NumPy. Okay, so as we applied a element-wise multiplication with A and mask, and divided by the probability, we will basically scale up the activations a bit by some expected value. Okay, so we can observe that in the previous example, all these activations, they are below 0. Okay, if you look at these two numbers, but here it's above 1.0. Okay, and there's some, of course, the two false here will lead to the zeros to the corresponding positions here. Okay, so that is the basically how dropouts can be implemented during the training phase. Okay, let's go to the next slide. And more the trickier parts in the backward propagation, right? Because we want to apply the gradients when you compute the gradients in the backward, because in the forward pass we didn't use all the activation layers because those units are dropped out. So in the backward step, we basically need to use the mask that we created in the training step, and we only compute the gradients that are with mask with 1 values, right? Because it's not used. The activations with 0 values, they are not used in the forward pass. So there's no need to update those units during the backward pass. Okay. So some other details about dropouts. First, the probability to keep the units may be different, may vary across layers. Okay, so this probability can be something that has a layer associated with it. So it could be some more complex hyperparameters, some additional hyperparameters that we define at the beginning. Okay, and so for the layers that have more neurons, more units, we can basically drop more of it, right? And for the layers that don't have much connections, we can control the dropout rates by keeping more units in that layer. So I think in the case of large neural network models like the neural language models in NLP, the dropout rate is nowadays a kind of there's some fixed choices, and it's not going to significantly influence the results if it's by changing the dropout probabilities. So I think that if I remember correctly, for the LSTM models in Pytorch, the dropout probability is default value is 0.2 or something, and people don't usually change that values unless they have different needs, different motivations for having the dropout rate to be different, to be higher or lower. Okay, and also it's a kind of a default choice to always have some dropouts in neural network, because it really can effectively reduce the overfitting issue.
Can I ask a question? So is it true that you would use dropout instead of atom or the other ones, right? Like you kind of pick one optimization, optimization, or I guess this is regularization.
It's regularization. So it's not related to atom. Atom and momentum or RMSProp, they take effect at a stage of updating your parameters. So they are the way to change the gradients to alter the gradients you computed by making the gradients point more towards the theoretical minimum. To make the gradients more effectively pointing to the minimum points, so that making the training faster. So that's basically what Atom's goal is. The purpose of Atom is to make training faster and easier to converge. And for the dropouts, it has the same or similar goal as the L2 regularization. So the purpose here is different. The purpose for regularization is to reduce overfitting.
Okay, so would you use them at the same time as your training?
We can use the two different types of technique at the same time. That's totally.
I see, because they're doing different things.
Yeah, they're doing different things. That's totally no problem, no conflicts.
Okay, thank you.
Yeah, I know there's too many fancy names in this whole chapter after we introduced the deep learning, after we introduced deep neural network, and it'll take some time to figure out the actual motivation behind those terms. But basically, I'm trying to put the same techniques that serve the same serve the same goals into one category. For this form of regularization, would we use dropout before doing forward propagation on each iteration? So the dropout is actually done simultaneously as the forward propagation, because as you see, the activations, the computation of the activation for one layer is computed by this mask with the original value of the activation. So I think it's the immediately after some activation is computed, it will compute the mask and do the multiplication, and then pass the new activation to the next layer. Yeah. So I think it's a simultaneous process. Okay. So next, and for testing time, and when we use when the training is done, first of all, we have go through all the training examples, right? So when the new data coming, then there's no need to do the dropouts, okay? Because the purpose of dropouts is that the model will not fit to the training data so well. But now when it's testing time, it doesn't make sense to remove some units in the model. We'll basically need to use all the units. We need to fully use all the neurons, all the units in the network to make predictions, because we don't know what the testing data are gonna look like. Okay, we're gonna use all the possible information we have so far. Okay, so it's just a regular forward pass to make the predictions. So dropout is an amazing technique, and so if we look at the so I guess this paper is from the figure is from the original paper from where the dropout technique is first proposed. So it basically can reduce the error rates in testing sets. Okay, so without using the dropouts versus with dropouts, we can see the very huge. Well, from the perspective of y-axis, it's just the difference between 1%. But nowadays, the 1% difference is a very significant improvement in terms of the performance. And we can see it's a very consistent improvement, because when you train the data with more iterations, so in the case, the x-axis is the number of iterations. So the more updated iterations you give, then your model fits better to the training data sets. Okay, but a better fit to the training data sets will basically inevitably lead to some degree the overfitting problem to some degrees. But the dropouts seems to deal with this problem pretty good, because it makes sure that even though your model fits well to the training data sets, but your model has some randomness, has some innate random mechanisms that cancels out the special patterns in training data sets. It cancels out the chances that the model is memorizing the special patterns. Okay. Some more results as a comparison between dropouts in terms of the loss. Okay, the loss will continuously, like consistently drop as the training goes on, right? Which means the model is still keep learning, but not overfitting to the training data sets. And these results given, the dropout is a very, I would say, based on your, it depends on your data, depends on your problem. And I still want to use my experience about LSTM models with default dropouts, which I think is good. And usually you will need to keep the dropouts without disabling it. Okay, so if you disable dropouts, it's quite easy to overfit to the training data, and it's easy to not to observe a good training curve that the loss will keep decreasing. Okay. All right. All right, so for dropouts in Pytorch, it's just like the way we adapt the momentum, the atom optimizers. The dropout is also easy to implement, but it's not. It's within the model. It's not at the optimizing stage. It's in the model. When you define a model, you basically want to set how much dropout you want to have for each layer. So in this example, we have a simple 2-layer neural network. After the first linear inputs, we have the ReLU. So this is where the activations is computed. Okay, so we set a dropout with probability 0.2, which is to drop out 20% of the activations. We basically apply the dropout to that activation output from the ReLU. And then we connect to a output layer, which is also a linear layer. Okay, so I think this partially, this can answer the question of where dropouts, at which point dropout happens in training. So it's basically one part of the model. So it's one part of the forward pass and backward pass. Okay, but only the difference with NumPy is that in Pytorch it handles dropout as a kind of a special layer for you. You don't need to manually alter the activations or alter the backward gradients. Okay. All right. So the intuition behind dropouts. So we can talk more about it here a little bit more. And I think the intuition is very straightforward. Okay. So because the deep neural network is a huge model, it's just naturally have the risk of overfitting. So if we reduce the number of parameters or reduce the number of effective parameters during training, then we can naturally achieve the results of less overfitting, right? So, and another intuition is that we randomly remove elements, remove new units from a network. So that means we don't want that. In that way, we avoided the network to remember some certain patterns or certain features in the data. Okay, so the weights basically need to be spread out across all the networks. So, for example, in predicting one learning, one example in the training data set, in the first iteration, we're using some different weights as to the second iteration. So that means all the units are used to predict the same data example, okay, which is a good way to prevent the network to use some fixed units to remember some certain data points. That is very important if we want the model to be a generalized model, to be a general model that can recognize patterns instead of memorizing patterns. Okay. So yeah, and let's do a recap, and that's pretty much of today's contents. Okay. So dropouts is to avoid overfitting. Okay. So, and this may be a redundant, but if there's no overfitting, or if there's if the model is not that complex, then probably you don't need to use use dropouts. Okay, but unfortunately or fortunately, we have large models. We have very complex multiple layer models. Then dropout is basically a must have choice. Okay, and it is almost always used in computer vision applications. Okay, because we usually have larger models and we have less training data sets, and it's easy to overfit. Okay, so if you are interested, you can use the link to click to watch the talk by Geoffrey Hinton's talk over in Dropouts. I think he gave some wonderful analogy from the technique of dropout to some mechanisms in human the neurons in human brains. And Geoffrey Hinton is one of the deep learning gurus. He is a professor in University of Toronto, and his work on neural language models, sentence models, and deep learning way of natural language processing, and the application of Dropout in deep learning models is he's an expert in those fields, and he also won the Turing Prize, which is the highest prize in CS. I think it's 2 years ago, 2018. Okay, so that's our content today, and so I think I have one more slide. Let me check if this case. Yes. So let me cover these slides. So other than the L2 and dropout techniques, we can have other regularization methods. Okay. So regularization, the term regularization means that we want the model to be general, right? So the one cause of the overfitting is that we don't have enough data. So especially in computer vision, so why not we create some more data by using some augmentation tricks or techniques. So this is some common ways of augmenting image data before we feed the data to neural network models to conduct tasks like image classification, image captioning. So these image data, if we enlarge the size of the training data set by making some simple simple changes on the data, it's also a way to achieve the the goal of regularization, because we create randomness in the data sets, but we create some noise by basically removing the idiosyncrasies in the data, so that the models can be guided to learn some general patterns instead of memorizing the idiosyncrasy instead of memorizing the specialty patterns in the small data sets. Okay, so we basically covered regularization and learning rates decay as well. So I think in the next class, we're gonna complete our journey by talking about vanishing and exploding gradients, and more importantly, there's a special technique called a batch norm that we're gonna cover in the next lecture. And all right, so that's pretty much the content of today, and thanks for coming. I think we have some good questions raised here.
Thank you.
Yeah, thank you.